Eccoci, allora intanto buonasera a tutte e a tutti, grazie per essere qui così numerosi in questa magnifica sala, la Sala dei 40, l'Aula Magna dell'Università degli Studi di Padova. È un piacere per me essere qui, è un piacere vedervi così tanti. Qui abbiamo molti ospiti stranieri per lo European Lunar Symposium. Così io adesso switcherò, si dice così, cambierò e passerò dall'italiano all'inglese. Quindi parlerò piano e io spero che tutti voi, se poi ci saranno insomma anche delle domande, cercheremo di farle in inglese, ma se qualcuno avrà una domanda in italiano possiamo poi tradurla. Good evening to everybody. I'm very happy. It's a great pleasure for me to be here this evening, this afternoon. And it's a great pleasure also to see how many you are with us today. Before going on with our program, we would like to have some formal greetings. And I begin from our host. And as delegate of the rector of the University of Padova, Professor Daniela Mappelli, we have with us today the pro-rector with responsibility for research, Professor Fabio Zwirner. Please, Professor Zwirner, the floor is yours.
Well, good evening to you all, and a warm welcome also on behalf of our rector, Daniela Mappelli, who is not in Padua today, for today's public event, Next Footprints on the Moon. I have a personal recollection I can't avoid telling. The first footprints on the moon happened when I was 11 years old, and I see many young people among you. In those time, 11 years old boys were not allowed to go to bed after 9 in the evening. So I had to fight a lot to obtain from my parents permission to stay up to watch the first footprints on the moon. And indeed, I'm very glad that that permission was given, because it was one of the most emotionally involving moments of my youth. So coming back to our event, I would like to welcome, first of all, our distinguished speakers, Dr. Maurer and Dr. Carpenter from the European Space Agency, and Dr. Schmidt from NASA, and Dr. Mugnuolo and Dr. Crisconio from the Italian Space Agency. I also welcome those of you who are participating in the 3 days European Lunar Symposium. Professor Piotto has already told you at the opening of the symposium, but I repeat for those of you who were not there, that we are very proud for hosting the first in-presence symposium of this series after COVID. And for this, I thank the International Organizing Committee, of course, and the local organizing committee, who have done a lot to set up this symposium that I hear is very successful. And of course, welcome to all colleagues, students and citizens and young citizens who are here today. So Padua has a lot to do with space activities in general and the moon since its very beginning. You know that the University of Padua is 801 years old. And just to mention a few, Copernicus, Nicolaus Copernicus, was a student here from 1501 to 1503. And of course, the famous Galileo observation of the moon in 1609 with his telescope was made from his home a few hundred meters away from here, walking distance from here. The precise location is not absolutely sure, although there is a plate on a house in Via Galilei, saying that that was Galileo's house, but in any case, we know for sure that it was walking distance from here. But in modern time, of course, Padua has been involved intensely with space activities and with activities related to the moon, thanks to its University Center for Space Activities, who is now directed by Professor Piotto, after the direction of the late Professor Stefano De Bei. And Professor Piotto has already described to you the activities of this center that we value very much during the conference. Just to mention another person in recent times who is famous in the space community, our Center for Space Activities is entitled to Giuseppe Colombo, who was a professor at the University of Padua. And these days, we are, of course, this I don't say for the experts who know this better than me, but I say for the general public. The university is giving a lot of attention and importance to space activities. We have long-standing collaboration with the Italian Space Agency, our agreement was recently renewed. We are participating under the umbrella of the Italian Space Agency with other universities, research centers, and industries in a so-called extended partnership in the context of the National Recovery and Resilience Plan. And we are also involved in what is called a regional aerospace innovation network that is trying to improve the collaboration between industries, universities, and research centers in the Venetian region and more generally in the Northeast, that includes the three Venetian regions called Triveneto in Italia, to go farther and farther with this. So I think I should stop here. I don't want to subtract time from our speakers. I will stay here with you to listen to them. So welcome again, and I wish you a very successful event.
Thank you, Professor Zwinner. And on behalf of the Mayor of Padova, we have with us today the City Councillor, Dr. Bruno Cacciavillani. Please.
Thank you. Good afternoon, everybody. I am Bruno Cacciavillani, City Councillor, and it is my great pleasure to convey greetings on behalf of the entire administration, particularly from our Mayor, Sergio Giordani. I would like to express my gratitude to the Director of the Department of CISAS, Prof. Giampaolo Piotto, for the invitation extended to me. I was even in my parents' thought during the first footprints on the moon, so it is an honor for me to be present at this significant event, Next Footprints on the Moon, and to share this room with the international professors, engineers, and scientists. I cannot even compete with the scientific and academic personalities and preparation present in this room, so all I can do is thank you for your work. The international reputation of the city that I represent, of the city of Padua, has deep roots, and the name of the already mentioned Professor Giuseppe Colombo, founder of this department, is already in the history of world astronautics, especially now with the probe bearing his name exploring the planet Mercury. I would also like to dedicate as a thought to Professor De Bei, already mentioned. Lastly, I would like to express my gratitude to underline the importance of the work of this department, not only for Padova, but for the entire Veneto region and the nation. You have managed to create a regional industrial network where many companies have established and will continue to establish their work and their roots. Moreover, thanks to the success of the University of Padova in this space project and in other space projects, it brings forth a myriad of opportunities for our community. It ignites the flame of inspiration within our young minds, encouraging them to pursue careers in science, technology, engineering, and mathematics. It attracts talents and investment to our city and our region, fostering the economic growth and innovation. It cements Padova's place on the global stage as an hub of scientific excellence. Thank you once again, and I'm delighted to be present at this wonderful gathering this afternoon. Thank you.
Thank you, Dr. Cacciavillani. And finally, one of the partners of the Lunar Symposium, of the European Lunar Symposium, and of this event of this evening is also the National Institute for Astrophysics, Istituto Nazionale di Astrofisica, for which I work too. And on behalf of the director of the INAF, Astronomical Observatory of Padova, we have the deputy directors, Dr. Simone Zaggia, that will give us a formal greeting. Please.
Good evening to everybody. It's my pleasure to be here and to give the greetings of the Istituto Nazionale di Astrofisica and of the Observatory of Padua. And also my time to share my memento of the lunar footprints. I don't remember the first one because I was too little, but I remember the last one, the one of the Apollo 17 in 1972, it was 7, and so I remember that I have seen on the TV, and I'm still waiting for the next one, so I'm really eager to see the next footprint on the moon. And going back to my greetings, National Institute of Astrophysics is extremely committed to support every kind of scientific, technological, also outreach initiative aimed at going back to the moon and trying to increase our knowledge of this body of our solar system, so nearby to us, but still so unknown to us. There are a lot of personnel in INAF, in several institutes. National Institute of Astrophysics is divided in 17 institutes spread all over Italy. And in many institutes, we have entire research groups that are working on this. Here in Padua, we have a strong group that is strongly committed to support scientifically and also technologically this endeavor. And so for us, for INAF, that is also supporting strongly the Lunar Symposium here that we are hosting this evening with the public event. And so for me, it's a pleasure to be here and to give you my welcome to everybody and to follow the today debate that we will have in a few moments. So thank you very much and have a nice evening.
Thank you, Dr. Zaggia. And now to introduce one of our main guests of this evening, I call Professor Matteo Massironi, who is one of the mind of all this Lunar Symposium and of this event, a planetary geologist, and I leave you the floor, Matteo.
Okay. Thank you. Yes, I organized the European Lunar Symposium today, but the European Symposium has a long history. It's come from 2012, so it's 11 years that it exists, European Symposium, and thanks to NASA Survey and Mahesh Anand from the Open University that have thought about this beautiful event for all the lunatic, okay, all the people that like the moon. So I am here to introduce Matthias Maurer. He's an ESA astronaut. He's an European astronaut from Germany. He joined the ESA astronaut corps in 2015, and he went to the International Space Station in 2022. And at the end of the 6 months there, he was, I would say, substituted by Samantha, and you met her there. Before being an astronaut, he was a material scientist. So he took a degree and a PhD in material science and other studies. So he knows very well materials. I had the honor to be one of the instructors for him about the field geology. Okay, so we funded this course that is called Pangaea. Pangaea is the last supercontinent on the Earth 250 million years ago. All the continents were together in Pangaea, but it's also something that I would say means planetary analog geological and astrobiological exercise for astronauts. So just after 1 year, he was appointed as astronaut. He followed this course in preparation of the future exploration on other planetary bodies. So we enjoyed a lot together going to the field, and he is one of the people, of the astronauts, that look into a landscape he can describe the landscape. He can find the right place to study and sampling, so the sampling site, and he can even choose the sample and recognize the different rocks because of that. And also I would say that I'm sorry. So I think I've said more or less everything. So it's a pleasure for me to introduce Matthias. He was also, sorry, I didn't remember, he was also project manager of the Luna analog site, so a lunar simulator, so an indoor analog site for testing the instruments and training the astronauts. So I think he's the best person that can introduce you on the future next footprints on the moon. So I leave the stage to Matthias. Thank you.
I think I have the headset. Yeah. Buonasera a tutti. Good evening, everyone. It's my pleasure to be here in such a most distinguished room where Copernicus and Galileo research studied and basically paved the way that we today can do what we are doing, dreaming of flying to space and actually flying to space. In the next 40 to 45 minutes, I would like to take you on a journey on what it needs to fly to the moon. And I will also give you a little bit of a human side on touch to it. I also will talk about science, but you're the experts, so I will keep it on a very low level. I was in space in November 21, that's when I launched, and initially it was foreseen that the Artemis 1 mission would launch before Christmas 21 to space, and we were already talking and discussing in space, can we take photos from there? The launch from space, it's a unique point of view. In the end, it was delayed, and it launched only last year in 2022, but it was a huge success, and with Artemis 1, we proved, or NASA proved the technology. And so everything now is up and ready and set so that Artemis 2, the very first mission, when we send humans again for a flight around the moon, can launch. And that will take place in 2024. And you see on the slide my 4 colleagues, Reed, Christina, Victor, and Jeremy. Jeremy from Canada, the rest are Americans. We are a small family, I know them well. I trained with Reed exploration of Mars in an underwater mission. We lived together for more than a week. Well, I stayed for 2 weeks, but he left after 1 week. Christina was responsible for my mission as crew interface. With Victor, I trained underwater and BL runs to do spacewalks. And Jeremy and I, we were both part of the 2009 selection. The journey will take these 4 around the moon. It's roughly 10 days, a flight around the moon, on the big rocket that you see on the slide. And this journey will take them inside the Orion capsule. This is actually Orion of the Artemis 1 configurations. So you see 2 dummies in there that were used to measure radiation in the moon environment. But imagine the person here in the orange suit times 4, being in there for 10 days. One needs to go to the toilet, another one does sports. So it's a nice and cozy environment. And, and you actually get to know each other pretty well after 10 days, I would say. So it's not all fun. And sometimes you also need to do stuff and train stuff that is useful, but it's not so glorious. And so my contribution to Artemis 2 mission was to test a procedure of what happens if the toilet fails. So imagine there's a toilet in there, and I explained it always very easy. When you're in 0 gravity, everything floats. So you want to have stuff not floating around you, definitely. So that's why you attach a vacuum cleaner to a toilet. And so then usually the toilet works and everything floats into the right direction. But what happens if the vacuum cleaner doesn't power up and there is no air drag? And I had to test this procedure on the ISS as part of this mission, Artemis 2, and there are solutions. Okay, I'll leave it with that. But let's step a little bit back. Why are we actually flying to space? Why are we flying towards the moon? What's the objective? I mean, in 1969, people have been there, and they figured out, well, there is sand on the moon, and there's a flag, so we did everything. No, didn't we? No. With all the missions, unmanned and manned missions, we brought back so many samples, and now we have so much information, and most of you are working in this area, know it much, much better than me. The moon is very interesting. It has a lot to offer, because it's more or less the same age as our planet Earth, but contrary to planet Earth, the surface is fixed. The Earth has climate, it has tectonics, it has volcanism, it has weather. And so the surface is more or less fresh. And if we want to look back into the history, the moon is a good place. And so we can learn a lot about the origin of our solar system. And by learning this, we can also learn how life started on our planet and maybe where we should look in our universe to see another planet similar to Earth, with conditions for life. But we also can fly to the moon and set up telescopes that help us to look further back into our past than the James Webb Telescope. So into the ages that we call the Dark Ages, or the beginning of the cosmic dawn. And once we've done all the scientific part, which should always come first, we can also say develop technology, because we don't want to stop at the moon. We want to fly further. We want to fly to Mars. And maybe later, also further than Mars. But in order to do so, we need to develop technology. Because flying to Mars, we cannot just bring everything that we need in our rocket, because then the rocket is basically full with just the food to fly out there and the fuel to go back and forth. It's much, much better if we learn how to fly to Mars and to make use of the resources that we find there. Resources that allow us to breathe, to drink water, to build a house where we are protected against the space radiation, and also where we can work and do scientific stuff on the inside. But also where we can produce energy to run the entire equipment. And then also produce the fuel to fly back. So these are the purposes that we want to do out there, and Mars is not the best place to test it, because it's a journey that takes 2 years. And if we find out that on Mars the technology doesn't work, then we have a massive problem. If we find this out on the Moon, it's a 4-day journey back, and okay, bad luck, but that's why we chose the Moon also as a testbed for our technology and the in situ resource utilization. So Artemis, a roadmap. Artemis 1, I already mentioned it. It was a flight unmanned around the Moon. Artemis 2, 2024, will bring the first 4 humans, again, close to the Moon's surface. There will be no landing, there will be no intermediate stop. And then there will be Artemis 3. Artemis 3 is currently planned to be a Moon landing. Between 2 and 3, there's also another event drawn into the schedule. It's the first launch of modules for the new station, which we call Gateway, which will fly around the Moon. And in later missions, astronauts will fly to the Gateway and work on the Gateway, and also from Gateway land on the Moon. So it's an intermediate stop. This intermediate stop allows us to reach every point on the Moon, also the polar regions. But Gateway is more than this. Gateway is also a spacecraft, because in the future we want to travel to Mars. And so we need to learn how to operate a spacecraft that is very, very efficient. On the ISS, for example, we recycle water. 92% is currently the rate. Sounds pretty good, but the 8% that we lose, like on a 2-year journey, it's quite a bit. So we need to get better in the recycling rate. And we also want to raise the orbit and change the orbit of the Gateway, and there we need more efficient propulsion system, and that's also another part that we want to test there. So we will have the Gateway, and we will have the landing on the Moon. And the landing on the Moon will be with unmanned missions and rovers, and later on missions with astronauts that have small vehicles, and later on even pressurized vehicles. Flying to the Moon, it's not only climbing into a rocket and off we go, it requires much more. So obviously it is the rocket. And on top of the rocket is the spacecraft that brings us to our destination and safely back. But there's also the entire infrastructure on the ground. The connectivity, the infrastructure logistics that you need when you're on the surface of the Moon. Namely, like the human landing system that allows you to land, but also the spacesuits and the surface mobility. And the Gateway I already mentioned. So I will explain these a little bit more in detail. The rocket that is foreseen for the Artemis program is the Space Launch System, the SLS. And Artemis 1 was a successful test flight also for this rocket. It is not the final configuration yet. So this rocket currently is able to bring around 26 tons to the surface or to the Moon orbit. And it will be used until Artemis 3. Starting from Artemis 4, there will be an upgrade of the upper stage. And so we will be able to bring more mass to the surface of the Moon, or close to the Moon, 37 tons. And even later on, there will be a further upgrade. The boosters will become more powerful, and then we can bring even more than 45 tons close to the Moon. The Orion spacecraft, and the photo that you see here is actually from the Artemis 1 mission. It's quite different from the old Apollo capsule. So it offers room for 4 astronauts. The Apollo had only 3. And it also needs to be like more resistant to the extreme events that happen when you come back. For example, when I came back from the ISS, you fly at 28,000 kilometers per hour. And when you enter with the spacecraft the atmosphere, temperatures of up to 1,900 degrees happen on the outside. So you have a heat shield. Without the heat shield, we would burn up. When you come from the moon, you have 40,000 kilometers per hour. And the temperatures are roughly 1,000 degrees higher, Celsius. So it's really, really hot. Later on, when we fly to Mars and enter from Mars, it will be again 500 degrees hotter than from the moon. So it is a significant step upwards for the engineers to protect the capsule. And so Orion is a new vehicle that was developed for this. In that photo, you see also the lower part of it. It's built in Europe. It's the European Service Module. And that's basically our contribution to the Artemis program, to also secure flights of European astronauts towards the moon. That's the vertical assembly building. It's a huge, huge building built actually for the Saturn rocket, like in the 60s. And the size limiting factor here is the size of the doors that you see open. It's 140 meters tall. So basically, the new rocket needs to fit in there so that it can be assembled. And you see this rocket easily fits in there. It has a height of 98 meters. The new version will be 110 meters. And once it is assembled inside, it needs to be transported to the launch site, and that is done by the mobile launcher that you see here on the photo. Basically, it's a platform, and on this platform is the tower. That's the launch tower. And this platform, it needs to be transported by crawlers that you see in the photo on the right-hand side. And these were also built in the 60s, so for the Saturn V. And all these systems need upgrades, because today there's way different infrastructure, way more sensors and actors and cabling. So everything needed to be renewed. And for the new rocket, the 110 tall upgraded version, there also needs to be a different mobile launcher platform. Launchpad 39B. 39A is where I launched from with my SpaceX rocket. 39B is now where I would like to launch from for the next mission. It's the place where SLS launched from for the Artemis 1 mission, and all future missions will take off. And also this needed to have a significant upgrade. You see here 3 towers around the one in the middle. These are to protect the rocket against lightning, because it happened that Apollo 12 got a lightning strike, actually 2, during the launch. And since then, basically, we want to make sure that we don't launch if there's a thunderstorm in the vicinity of the launch pad. Because at that time, the rockets were a little bit more mechanic and more robust. But today, with all the electronics inside, we absolutely don't want to launch if there's risk for a thunderstrike or lightning. You also see the small, now it's a bit running fast. You also see the small tower there with the sphere on top, and that contains water. And that's the water that we need when the engines light up. You pump a lot of water to protect the concrete, because the rocket engines, they're so powerful and so hot, you actually melt a lot of concrete away. So you damage always your launch pad. And that's protecting. On the right-hand side, you see the capsule after the landing, or the splashdown in the water, and the recovery ship that pulls up the capsule after the landing. And in my flight, I also landed off the coast of Florida in the water, and I can tell you, after a wild ride through the atmosphere down back, and you splash down on the ground, and then you feel like you made it, but it's actually the movement of the sea that makes you seasick after the wild ride. And such a capsule definitely is not a good boat. And if something happens during the launch, we are trained that we need to sustain up to 2 days until we are rescued. So imagine 2 days in such a small capsule in the middle of the ocean. It's definitely nothing that I would like to look forward to. Up, fast. Here we have the Lunar Gateway. That's the station that will fly around the moon. And we want to fly towards the gateway, dock to the gateway, and then we either do some research work on the gateway, but we also switch from the Orion capsule to the lander. And then with the lander, we land on the surface of the moon. You see certain elements in green. These are the European contributions. It's on the left side, the European Service Module that I already mentioned. That is the propulsion system and energy system for the Orion capsule. So without the European contribution, the Orion capsule would not be able to fly to the moon. So we are really on the essential pathway towards the moon. Then we have 2 modules on the gateway. One is for habitation, it's called IHAB, and the other one is Esprit, it's for refueling the station. And there's also a small element that is for telecommunications. The first module that will be launched between Artemis 2 and 3 is what you see on the left side, where the letter Esprit is written, actually the part in gray. That's the power module and the HALO habitation and logistics module. The text below shows also what the current planning is. So Artemis 1 and 2, well, 1 is already done, 2 is already fully planned, and then we will have the launch of the core of the gateway. Artemis 3 will be the first landing. Artemis 4 and 5, you see green elements. So it's European contribution. And that is why we will have on both of these flights a European astronaut on board of the spacecraft. That can be Samantha Cristoforetti, Luca Parmitano from Italy. It can be Thomas Pesquet from France, Alexander Gerst, me, or Andy Mogensen from Denmark. So we are the 6 that are currently in the Artemis astronaut team of ESA, and that's also why I wear my shirt with the Artemis logo on there. We have a third flight that I forgot to mention, and the third flight is not yet defined, and we hope that the first European will be on the surface of the moon like before 2030. The human landing system. So far we have launched, we flew to the gateway, and we're there. We're flying around the moon. How do we get to the surface? That's the human landing system. Oh. We get there. I guess many of you followed the launch attempt from the Starship, SpaceX, a few weeks ago, or months already ago. And the Starship is actually what we will be using to land on the moon. It's one of the 2 companies that had been selected, actually the first that was selected, and now there's a second one. The photo in the middle shows you the version of the Starship, how it is supposed to land on the moon. And in very, very small, on the bottom, you see also people. And so you can imagine this is not like the Apollo lander. It's not the Eagle. This is a huge, huge lander. And so it even has an elevator, because otherwise you wouldn't get down to the surface. So, and this, in the scenario, it will remain in the moon area. So it will not fly back to Earth, and it is refueled. And to refill it, there is a tanker version of the Starship. So here you see Artemis 3 foresees a landing on the moon. A landing with a Starship that 2 months ago exploded in the first test flight. So I guess every one of us understands there's a lot of flux in this planning, and before the Starship is not fully successfully flying, I don't see that we will go for a launch attempt. So that's why I already see that Artemis 3, it's planned to land on the moon, but I wouldn't be surprised if it shifts a little bit and the mission itself gets a different priority. In the last few days during our conference, we talked also a little bit about the Argonaut, or EL3. That's the European lander that we plan for the moon. It is able to land at least 1.5 tons in certain presentations. You also heard like mentioning 2-point-something tons. So it's a project that has been approved in the Ministerial Council last year, and it is currently in development. And we hope that this will enable European payloads, European experiments to be flown and landed on the moon, but it's also a part of our barter with NASA and part of the entire ecosystem on the moon, that we deliver cargo to the surface of the moon. Once we're on the moon, we can walk, but we also can take a taxi. And that's the idea that we have here. So there is currently a rover in the planning, a vehicle that astronauts can sit on or stand on and drive across the surface of the moon, unpressurized. This vehicle, whenever the astronauts are not on the moon, it can also be used for robotic operations. So it can pick up an experiment, a payload, or it can bring it to another site. It can also be used to drive around a little bit like the rovers that we have currently on Mars. The astronaut here in the right picture is kneeling down, so it's like on one knee and can actually hammer on the rock and do stuff. With the current spacesuit, this is absolutely impossible. So last year I had my spacewalk on the ISS, and the suit, it's an absolutely limiting factor. It is, you're inside a football and it's inflated and it's stiff. And you have huge gloves and everything that you need to grab, it requires a force. And I was 7 hours outside, and in the end, my arms were absolutely sore. So whatever experiments you are planning, just consider there's a guy or a girl inside the suit who has to do what you're doing. And you cannot early enough involve the astronaut colleagues to say, like, is this concept that you are currently planning and thinking of, is it actually feasible? The suits will be better. Currently, NASA selected 2 new providers, and I heard that the suits are way more flexible, but nevertheless, 0.3 bar inside means it is inflated and it is and remains rigid to a certain level. In a later version, or later Artemis mission, we will also see camper vans on the moon and a pressurized rover. And using such a camper van on the surface of the moon will allow us to travel long distances and go from site to explore. And astronauts can then land on one place, do their 3 to 4 weeks excursion on the moon, exploration mission, and then the rover can ideally also be remotely driven to the next site up to 1,000 kilometers away, and then the next mission could take place as a concept. And on the right-hand side, you see that JAXA is currently preparing such a mission, I believe in cooperation with Mitsubishi. The exploration hardware, I already mentioned, is a lander, a pressurized rover, but in the long run, we want to have a base on the moon. And a base on the moon, I imagine it a little bit like a research station in Antarctica. In the very beginning, people asked, like, what do you want to do in Antarctica? There's just ice. There's nothing to do. Nowadays, we have so many Antarctic polar research stations, and I believe the largest one, McMurdo, a US station, has more than 1,500 scientists in the summer. So there's a lot to do. And I expect the same story will happen on the moon. So we will go there will be a small house, there will be maybe 4 astronauts, scientists on the surface of the moon, and we will discover there's a lot to learn here, and even more to learn. And we want to have a larger station because more scientists need to come. So it will be the beginning. It's not an end story. Have one house for people, and we are there for like one mission, and then we go home. I think this will be a permanent base for astronauts on the moon. It might not be like permanently inhabited with astronauts, but we will always come back and do research and do more. So these are the points where the Apollo landings happened, and now you see that's the area where we want to fly to in the future. The polar regions, especially here the South Polar regions. And you already see that in the equator area there was everything nice and sunlit, but here we have shadows, dark areas, cold areas. And cold is a good reason, because we think we can find volatiles there. So we find water that we can use to drink, water that we can use for energy, water that is rocket fuel. But in such an area, it is also completely different to explore than in the area where the Apollo astronauts went to. In the dark areas, it's so cold that the current hardware probably wouldn't work. So in the inside of such a crater, there are temperatures down to 25 Kelvin, I learned during this conference. So I don't think that the materials that we have in our spacesuit would protect us. Actually, the spacesuit doesn't have a heating system, the current one. It has a limited one, only for the hands. And when I did my spacewalk, we had a short, so we said like, okay, Matthias, can you do the spacewalk without the heating? Yes, I can. During the mission, I had cold hands, and they're like, hold it to the sun, and the sun will warm you up. I say, good luck in a permanently shadowed area if you want to warm up your hands. So there are fundamental questions. If you have humans in the loop, exploration will become more challenging, but will also be more rewarding, because the human can also do stuff that currently rover or machines are not able to do. This is a simulation of how it will look like for astronauts when we walk in the polar regions. When the sun is very low on the horizon, you will have shadows. In the shade, it's not like here on the ground where the atmosphere, like it still allows you the scattering of the light, that you, even in the shadow, is enough light that you see what's in there. On the moon, if there's the shadow, and you put some stuff down there, you will not find it. It's absolutely dark. So if there's shadow in front of you, you don't know, is this shallow or is this like a deep hole? So exploring, walking down there will be very challenging. And it's not like us, like here in the room walking. It's like you're inside of a spacesuit. You have a limited field of view, and if you have stuff hanging in front of you, it's even more limited. So we need to include this into the training. Here, another simulation of how it could look like with a very strong shadow and shade. So we work on the training to prepare our astronauts. This is a photo from the Apollo era, somewhere on the moon. And at that time, the astronauts were prepared on the ground, and then they were sent to the moon. They had voice communication, and at certain areas they also had video communication, but in a very poor quality. In the future, we will have much better connectivity on the moon. We already learned there will be satellites flying around the moon. One is called Moonlight, a European project, but we also have other commercial projects. So there will be connectivity, there will be communication. And the idea is that we bring the scientists along. Not in person, but virtually. We set up cameras, and then we will involve all the scientists on the ground in the actual exploration. And that's what we partially train already in the ESA geological field training. And Matteo, sitting here, he's the brain behind this one, also with Riccardo and Francesco. So it's a cooperation between ESA and the University of Padua. And for us, astronauts, in the beginning, it's important to learn the language of geologists, how do we describe an area? How do we describe the geology of it? And how do I find which of these rocks that are lying around me is the good rock and which ones I shouldn't bring home? So it's learning about geology, learning how to explore and how to describe, but also learning how to work together. Because on the moon, we have probably 7 hours in our spacesuit. 7 hours that I can do stuff, or I can just wait there until I get an instruction from the ground. So I believe all the scientists here that go to a field trip, usually you take your time, you observe, and then you think, and then you take decisions. We don't have so much time on the moon, so it all goes fast, fast, fast. It needs to be pre-planned, because time is oxygen, and oxygen is the limiting factor. Yeah? So we need to work together to find an optimum, so that you get your science, and the most science in the available time that we have. We also will have new instruments, and you see it here on the photo on the bottom side where I'm with my colleague playing to explore the moon. And these handheld instruments will allow us to screen, to decide, okay, is this a sample, and I take a sample value here, and that's good enough for you? Or do you actually tell me, hammer, and bring me a sample back home? This will take time, but then you have your sample on the ground. So it's a trade-off. And you on the ground, the scientist, you will need to tell us what is useful for you and what is enough to have just a quick measurement with the handheld devices. Here our team again in the Lofoten Island. So we train in Lanzarote for the volcanic areas. In the Lofoten in Norway, it's for the Anorthosite area. And then we also train in southern Germany for impact craters in the Ries area. And to complete the training, we also go to the Alps, but that's geology that we don't expect to find then on the moon. So also the Apollo astronaut trained here in the spacesuits, and I believe from the buildings in the background that could be Houston, JSA, I'm not sure. So they're here in their spacesuit, and there's a rock, and I believe they're really suffering in there, because these suits are heavy, and they're hot, and well, they probably didn't like it, and that's why today we do training in zero gravity, or training for zero gravity, and also training for the moon in a way that we get offloaded. So we can offload an astronaut by putting him underwater. And this here is a simulation of how we would explore the moon by being in a pool. Okay, that offloads you, but you all know that the moon is dusty, and dust and water doesn't really fit well, so it has a certain drawback. Also, on the moon you have a gravity of 1/6, but here in the water you have water drag, so you're way more stable. So it's also an offset. And that was too slow. And you also have different lighting conditions. I go back one. Different lighting conditions. Underwater, the light is not ideal. So I mentioned before, if you're on the South Pole, you have very strong shadow. Underwater, this gets diffracted. So you can practice a little bit underwater, but it's definitely not the most ideal way. So what did the Apollo astronaut scientists do and technicians? They developed a kind of a gravity offloading here with the car. You see a tower on the car, and there's the astronaut hanging with an offloading system. And the right photo, I don't know exactly what it is, but I believe he's walking or running next to the car. So that's an interesting approach to it. I'm not sure if you can use that setup to go actually in a volcanic field and to explore it. So that's why my NASA colleagues developed a different system for gravity offloading. So how can you train not under the water, but offloading, because the suit is very heavy, at least 130 kilograms. And so they came up with a system that is called Argos. And Argos is also used to offload completely. You can float in this system, and you can also reduce it to a gravity level similar to the moon or to Mars, if you want. And on the right-hand side, you see a colleague practicing the collection of samples in something that resembles the moon. The system, however, is limited to one person, and you have a limited test area. You can practice easy stuff like walking down the ladder. Needs to be practiced. You can also practice stuff like deploying experiments, setting up a base, setting up your science equipment, and so on. And you also, like always, want to do it in the real configuration, because if you do it without the suit, it's not as meaningful. So that led us in ESA thinking, okay, there is a need. There is a need for a new facility, because when we go out to the field with Matteo, we learn in 1 week so much about what the problems are, what works, what doesn't work. And so we decided we want to have the field trip with Matteo available 24/7, all year round. Without Matteo, because he's busy here teaching. But we thought we want to set up a facility, which we call Luna, which has all these elements, the elements that you see here in the slide. It provides you an area that is relevant with regolith, where you can have your rocks, an area where you have light conditions, like on the moon, with the strong shadows, and where you have gravity offloading, and where you have the interaction with the people and experts on the ground control, and where you have a scenario where people are really like in a mission. And the photo on the left, on the bottom, is, I believe it's Desert Rats. It's a NASA field training where you put candidates in there to check if experiments and procedures are fully relevant as in flight. So, and the result is what you see on the bottom right, our Luna facility. And I want to explain this a little bit more in detail. The facility will be located in Cologne. This is our campus. The European Astronaut Center is in the bottom right. And next to it, we have ENVI-Hub. It's a facility where we do a lot of bed rest studies, and NASA is a regular partner there in studies. The entire campus is right next to the Cologne airport. And the European Astronaut Center is the only place in Europe where astronauts are trained for space. And everybody who's flying to the International Space Station comes to us to get training on the European segment, on the European elements, like the Columbus module. On the bottom left, we will see Luna, and we have a lot of other institutes that are important for spaceflight. So it's a kind of a mini campus, a mini JSC. This is a video animation of the facility, how it will look like. It will be ready next year, 12th of April, so for Juris Night, the building. And then the outfitting needs to be done. So by the end of, or mid next year, we start operations in the Luna facility. It is a building that has an area of around more than 700 square meters of regolith. And we have the sun simulator that you see here. We will have meaningful collection of rocks so that you can come and test your scientific equipment. We will have also like mock-ups of the lander so that we can test procedures like unpacking, unloading. And we will have a dust lab and a gas lab to do in-situ resource utilization. On the outside, there will be, in a further evolution, there will be a kind of a small moon station. And basically, we want to do everything in Luna from the moment the Eagle has landed until the Eagle takes off again. So everything that happens on the moon surface, we want to train in one go here in Luna. And the best of it, Luna is free of charge. So you don't need to have a grant, you don't need to pay a lot of money. If you have an experiment that you want to test in an environment with astronauts, with other scientists, with other equipment, you come. It's a little bit like a picnic. Everybody brings his experiment, his or her expertise, and then we all work together and we practice moon. And I guarantee you, like in a 1 week simulation run, you will learn so much about how you experiment, how your expertise fits into the overall context. Okay, so that's a photo again, a still photo of what we want to do. And a summary. Luna is open, not only for astronauts, it's for science and academia, for industry. Also visitors will be involved there, so we have also outreach possibilities during the night, for example, when nobody uses Luna. We can have student teams remotely using it with rovers, mini rovers inside, so there's a lot of potential inside the Luna facility. I mentioned the gravity offloading system, the sun simulator, the ground segment, and also the labs that we have. What I haven't mentioned yet is the deep flow area. One area will be up to 3 meters deep, so we can hide there, or like put stuff under the 3 meters, and you can come with your equipment and try to detect it. Yeah, so for prospecting experiments, this will be very, very interesting. We will have a larger rover that comes a bit later, but also smaller rovers for student interaction. An exploration medical system, because on the moon we need to be able to be better prepared for medical emergencies. On the ISS, if something happens, we can always say like, okay, within 24 hours we're in a hospital. We land, we bring the astronaut to the hospital. If it happens on the moon, no, it takes time to fly back to the gateway. From the gateway, it takes again at least 4 days to fly back to Earth. So we need to learn more. We need to have more expertise and more equipment to cover medical emergencies. You see EVA suits. This will not be the real suit that we use on the moon surface. It will be an analog suit that mimics kind of the constraints that we will have in the real suit. And I already mentioned external modules that will attach to it. One of them is the Eden Luna. It's a module that has been in Antarctica. It's a greenhouse, and that will be one of the modules that we use then to grow plants and do related experiments. Luna offers also the possibility to have mixed reality. So using virtual reality, augmented reality, we can have a combination between the real experiments, but also using the modern technologies to simulate stuff that is not there in physical. That's a photo from Apollo 8, 1968. The astronauts flew to the moon. The first astronaut actually flying around the moon. And they reported afterwards, we came all this long way to explore the moon. And what we discovered, the most important thing, is planet Earth. And this is also true when you fly to the International Space Station. And looking down from outside, looking down to our beautiful planet, it makes you feel really, really humble. And it makes you want to protect this planet Earth. It's the only base that we have, the only place where humans have ever lived, and everything that has taken place in human history is down there. And it's actually in a very small layer, just covered by an atmosphere that, to you, from space, it looks like a soap bubble. It's so fragile. And I believe when we return to the moon in the Artemis missions, the focus will be on the moon, but when we communicate to the public, the focus will be also on the benefits for planet Earth. And with this, I want to end. Thank you very much. Thank you.
Thank you, Matthias Maurer. Thank you so much for your talk, wonderful talk. I think that maybe someone of you has one question for Matthias. We have time for 2 or 3 questions. There are some questions for the public. One? Okay.
Thank you very much. I wanted to get your opinion on what you think are the unique opportunities presented by having people on Gateway that, say, aren't present and can't be done in Earth orbit. Like, what's the human advantage of having people there?
Repeat again, I didn't understand. Like, what cannot be done on the Gateway?
Yeah, what do you think is the sort of advantage of having humans stay and working on the Gateway, and what are the opportunities that aren't accessible in Earth orbit, say on the ISS?
Yeah. So it's a very, very good question. It's like we have the ISS. The ISS is a huge station, and in ISS we do research in zero gravity. A station around the moon, you also have zero gravity, but everything that you bring to the Gateway is so much more expensive. So a standard experiment where you just want zero gravity, you will bring it always to the ISS or to the follow-on station. But the Gateway will be outside of the magnetic field of the Earth. So you have a different radiation environment. A radiation environment that is also comparable to when you fly to Mars. So all the experiments where you want to see interaction of like the radiation on the human body or like on other biological systems, you could do on the Gateway. But also Gateway allows you to observe interaction of the solar wind with the Earth magnetosphere. So there is a niche for experiments that you cannot do on the ISS. But it's also the operational part. When I said the Gateway is not only a station, it's also a spacecraft. And so we need to learn how to manage such a station, because you don't want to fly in an Orion capsule to Mars. You don't want to stay like 2 years in that small capsule. So you need a kind of a station spacecraft. And so Gateway has this role as well.
Hello, I'm Maria Francesca Cecchi, and I'm a trainee at ESC. And I want to ask you two questions. The first one is, which type of activities has been already scheduled in the lunar environment for the astronauts? And if there will be a simulator for the radiation in Luna to understand the effects of the radiation during the activities. Thank you.
Yeah, two very, very good questions. My honest answer is I don't know. It's yeah, you see, like the Artemis program, it's a huge program. There's so many people involved, and you have experts everywhere. I was the last few years, I was out for mission training and then flying to the ISS. Now I'm involved in Luna. So I'm not involved what the current status is on the Artemis side. Maybe my colleagues can report on this later on. But there is currently a team working on the science for Artemis 3. I believe the call was out earlier this year. So there are people working on it. It's just I don't know. Yeah. A radiation source at EAC, I think a lot of people would be concerned if you have such a radiation source. But there are facilities where you can do radiation experiments. And I believe Aidan is probably the better source for this information than me. Yeah. So sorry, no answer to your question.
Another question?
Hi. So I remember for Apollo astronauts, they have to train to do activities on slopes up to 11 to 12 degrees. Do you have something like that as well?
So training in space is very important.
Slopes, like?
On slopes.
Yeah.
Training on slopes is currently not foreseen. What I know is that our colleagues from the medical division, they are thinking on having astronauts jumping on the moon. Well, it's like you need to know in zero gravity, you lose muscle mass and you lose bone mass. And the bone mass that you lose, it creates the risk, it leaves your body via the kidneys. And so it creates the risk that you form a kidney stone. And that's very painful. And it cannot be cured in space. And so if one astronaut develops a kidney stone, it's end of mission for everybody who's in the same capsule. Then in my case, we were 4 in the capsule, 4 would need to fly back. So we need to remain fit so that we can work on the moon, or later on when we land on planet Earth, that we can like continue our normal life, but it's also important for the mission that we remain fit in order not to develop such a disease. But on the ISS, we have not the possibilities, all the possibilities. So we have a treadmill, so we run, we have a bicycle, and we have a system where we can lift weight. And that allows us to keep healthy, to train all the big muscles, but it doesn't allow us to train the small muscles. And so we have some new ideas. The scientists or the medical experts, they actually would like us to jump because the impact is good for the bones. It reinforces the bones. But on the ISS, we do zero gravity research. So imagine you're the researcher and I'm jumping here, then you don't get good results. So that's why we are not allowed to jump on the space station. But on the moon, it might come. Now, walking on the slope is also important when you plan an EVA, because working in the suit is very, very hard. And it might also be that you work harder than your backpack, the life support system, can actually tolerate. Because, I mean, it's like when I had my spacewalk, it was for 7 hours. And I breathe oxygen and I exhale CO2. So, and the CO2 needs to be filtered out by the backpack in the system. So if I breathe out too fast and too quick, then I saturate the filter much faster. And it's not linear. If I breathe too hard, then it basically gets exponential consummation of my life support system. So I cannot stay 7 hours, I can only stay 5 or 4 hours. So we need to learn how hard is an astronaut allowed to work. And I know that I believe 15, 20 degrees walking on a slope is within the limit what a spacesuit allows you to do. Otherwise, you're working too hard. So you could probably climb down a crater, but you cannot climb up again. There are means for it. There's a kind of like an electric device, a winch that you can have, and that pulls you up, and then you walk. But you need these tools, and you need to measure it. So I'm not really sure if you're referring to health reasons or operational reasons when you said, like, do astronauts walk on slopes? Both. So then I hopefully answered.
Thank you. A very quick last question. Do you have a last? Okay. Very quick, because we have no more.
Hi, my name is Divya. I'm a PhD student from the University of Manchester. So most of the people here, we came for the European Lunar Symposium, and we are mostly geology-based. Just wanted to ask, because you mentioned a point about learning geology and all of that. Firstly, of the 6 members that you mentioned in the team, are there any geologists? Secondly, as a person who might not have been used to geology or rocks or anything of that sort, how easy, difficult was it for you to learn geology, distinguish rocks, and all of that? Thirdly, because one of the main, important factors for going to the moon is bringing back rocks or identifying rocks and all of that, why do we not have many geologists going for such missions, except for just one, Harrison Schmitt, who went as the only geologist out of the 12, astronauts? So why are we all doing geology, basically?
Yeah. Very good question. So I believe at the moment there's only one geologist eligible for flying to the moon. It's Jessica Watson. Watkins. So it's my NASA colleague. She came to the ISS together with Samantha Cristoforetti. She's the only trained geologist in the NASA and in the ESA team. So in my ESA team, there's also not a trained geologist. We have astronauts from different backgrounds. Some are pilots, I'm a material scientist, and we have a volcanologist, physicist with volcanic expertise. So what we do is we train the astronauts, and I think today we are in a much better situation than in the past, because we have all the instruments, the handheld instruments, and we have also like the camera systems. So imagine when we land on the moon, we will bring cameras, set up the cameras, and then you will have your 3D goggles on the ground. And then I will look at a rock, and you will tell me, no, Matthias, not this rock. Walk around, pick up this rock, because you can also explore the moon. And I'm your hands, I'm your eyes. No, your eyes actually is with the camera. But so you can interact with me, and you can, on the ground, you can walk around with your scientist colleagues, and you can actually explore and say, like, we need to send him there, and there we need a sample, and here we need a measurement, non-destructive, and there we need the measurement. But the sample's there and there. So I think we will have a different concept, the way we will work together. But most important of all, you are right, we need to train the astronauts well, so that we are in the field as able as possible. But we will probably never be as good as you.
Thank you. I want to thank again Matthias Maurer.
Yeah. Thank you very much. Thank you.
Thanks, Matthias. Thanks so much.
Okay.
Now we have 1 minute of working for the chairs for the panel, and we can start with the video. Be patient for a very short interruption, 1 minute or two, because now we are going to have the panel.